Hello guys. So today we start. Oh, nice. Hello.
Hello.
So today we start a new topic, which is alternating current, and it's important topic since alternating current network is like our everyday experience. So our power grid is based on alternating current. At Kazakhstan and also in Europe, the frequency of the alternating current is 50 hertz. And in United States, for instance, it's 60 hertz. So it means that alternating current means that the current and voltage both during the half of the period, each half of the period, they change the polarity and direction respectively, and the average current, average voltage for alternating current within one period is equal to 0. However, this is not true for electric power, which is delivered to some resistor in such alternating current signal, since we have current in the second power. That's why we don't care about the sign of current. It always positive. So there will be some net electric power delivered to a resistor. So our task within this course will be to understand what is going to happen when we apply alternating current power source to different circuit elements initially. It will be resistor, inductor, and capacitor. So how electric current will flow through these circuit elements. And then we will consider also electric circuit, which has a combination of all three types of electric circuits, elements, resistor, inductor, and capacitor. So this is our plan for pretty much whole week. At the end of the week, on Friday, I believe we will consider in details transformers, like converters of AC voltage of one voltage to another. So it could be either up conversion or down conversion, depends on the ratio of number of turns in coils, which of transformers consist of. And but yeah, that will be probably the topic of our last lecture in this week. So now we start with the introduction to the alternating current, and in particularly how alternating current will flow in a resistor to which we apply a alternating current power source, which delivers some sinusoidally changing voltage over time. So let me change the camera. And first we consider such simple electric circuit, which has this alternating current power supply and a resistor. So this resistor is R, and alternating current voltage, which is applied to this resistor by the power supply, is delta V equal to delta V maximum times sinus omega t. So we have some sinusoidal signal which changes with time, and here is angular frequency. We will talk about this a bit later in more details. So here we have some voltage drop of our over the resistor. So we will call it delta V R. So this delta V is so-called instantaneous voltage. That's our task to understand what will be the instantaneous value at each given time of this voltage and current IR, which flows through the instantaneous current, which flows through the resistor. So in order to do that, we need to consider Kirchhoff's loop rule. And for this electric circuit, assuming that we have just two components, we have such an equation, which will be delta V applied instantaneous voltage minus the product of instantaneous current and value of the electric resistor connected in this circuit. So this will be equal to 0. So it's Kirchhoff's loop rule, which means that the sum of all voltage, like electromotive force and voltage drops in the loop, they should be equal to 0. So we know that current, according to the Ohm's law, is the ratio of voltage and resistance. So this instantaneous current is instantaneous voltage divided by resistance of our resistor. And we know that this instantaneous voltage is described by this equation. So it's time-dependent function. So we have delta V maximum, like amplitude value, divided by R, resistance, time, sinus omega t. And this will be equal to I maximum times sinus omega t. And this is the equation which describes instantaneous electric current in this circuit through the resistor R. So this maximum current I maximum is equal to the maximum voltage divided by resistance. And for the voltage drop over the resistor, like instantaneous voltage drop over resistor, we can write that this is a product of instantaneous current and actual resistance of this resistor. So that will be I maximum times R times sinus omega t. So now we can, so we have two equations which describe electric current through the resistor as a function of time. And so this is this. And also we have voltage, instantaneous voltage drop over resistor R given with another function. So they are quite similar. It's just some additional term. Here we have resistance of active resistor, which is not frequency dependent, and it behaves pretty much in the same way as resistor in a circuit with DC current. So In order to highlight this, I will try to share my screen now with some, yes. So here we have two plots. On the left side, we have current and voltage. So this is current dependence over time and voltage dependence over time. We see that these two quantities, two parameters change in phase. Means that voltage and current reach their maximum value, and their minimum, like zero value, also their minimum values at the same time. So there is no phase shift between voltage and current at the active resistor, which is hooked up to the electric circuit with alternating current power source. On the right side, you can see so-called current and voltage diagram with these phasors. So phasors are vectors which their magnitudes are proportional to the quantities which they describe. So there is a phasor for current, phasor for voltage, and they rotate with counterclockwise with the frequency of the alternating current with angular frequency omega, and the projection on the vertical axis gives us at any time the instantaneous values of these parameters. So we see what is important, that they have the same phase. So they are always oriented with respect to this, for instance, with respect to horizontal line, they are oriented always in the same direction. So there is so-called the same phase of current and voltage. So this is the feature of behavior, some specific behavior of active resistor in a circuit of alternating current. And now next, what we need to discuss is so-called RMS current, which stands for root square, like root mean square, which gives us an opportunity to link the rules for alternating current circuit and DC current circuit in order to describe them with similar equations. So the thing is why we need this, because as you may see, for instance, electric current is changing over time. During half of the period is as like some positive direction. During another half, it has negative direction. So there is, if we take just average of electric current, that will give us 0. However, if we deal with the Joule length heat dissipated at active resistor in the alternating current circuit, that will not be 0. There will be some average value, because we deal with the square of electric current, and it never goes to square, never goes to negative. However, we see that current depends on time, and that means that power which is delivered to the resistor also will not be constant. That's why it's useful to find some value of electric current, like some magnitude of DC electric current, which will result in the same amount of energy delivered to resistor as it would be with some alternating current which changes over time sinusoidally. So in order to do that, we need to calculate some average value for electric power delivered to resistor, and then based on that calculate what equivalent of DC current we would need in order to get the same power delivered to the resistor. So let us try to do it now. Let me stop sharing. We go to another slide. And we know that average, so electric power, which is delivered to a resistor in the DC circuit, will be electric current squared times R. So this is standard equation, which we derived a long time ago. So then we know that instantaneous value of the electric power delivered to resistor will be also following this equation. So this will be power as a function of time equals to this instantaneous current IR square times resistance of the resistor. So we want to find some average power which is delivered to the resistor in such alternating current circuit in the scope of one period. And then we want to substitute this average power with some, like represent this average power with some RMS electric current, which is equivalent of DC electric current squared times the same resistance. From here, we will get what value for this IRMS we need to take when we deal with sinusoidal alternating current. So now let us calculate this average power delivered to resistor in an AC circuit with sinusoidal current. So P average will be equal to 1 over T, where T stands for the period of the of this alternating current, an integral of from 0 to T, so we consider one period, and here is the product of IR times R, so IR squared, because we consider power, times dt. So this part, this integral, stands for total energy delivered to the resistor in the time interval from 0 to T, so during one period. If we divide this by T, length of the period, then we get some average power which is continuously delivered to the resistor during the period, one period. And of course, it can be translated for many periods because they are all repeating, they are the same. So we know from previous slide the expression for this instantaneous electric current, and let us put it here in this integral. So it will be 1 over T times integral from 0 to T times I maximum square times resistance times sinus square omega T dt. So now we need to integrate this. We know that I maximum and R, they don't change. These are constants, so we can factor them out from the integral. It will be I maximum square times R over period T, integral from 0 to T, 1 minus. So here we want to represent sinus square omega t in a different form according to trigonometry identity in order to solve this integral. So sinus square omega t is equal to 1 minus cosinus, here is 2 cosinus 2 omega t divided by 2 dt. So now we have two integrals. Will be I maximum square times R divided by T. Here we will put parentheses. Integral from 0 to T dt minus integral from 0 to T cosinus 2 omega t dt. So these integrals are now simple. We can take them, and that will give us the result. I maximum squared times R divided by T. Here will be just T, and here will be minus sinus 2 omega t divided by 2 omega. And this will be from 0 to t. So we need to recall that period is equal to 2 pi divided by omega. So it means if we substitute 2 pi divided by omega in the argument of sinus, omega will be, instead of t, omega will be canceled. There will be just 4 pi. And we know if it's fractional to the pi, sinus is equal to 0. So it will be just 0 minus 0, because sinus of 0, when we put 0 instead of t, it's also 0. So this will be just 0. And eventually we get the following. Let's go to another slide. So this will be equal to I maximum square times R divided by T. And in parentheses, which we had previously, there will be just T. So we cancel out this T. And, oh, sorry. Let's come back. I missed 2. So here we had this 2, so we need to factor it out from the integral. So we should have already here 2, and here we should have 2. Now we go next here. So here we have 2 in the denominator, and that means we have I maximum square times R divided by 2. So this is, as you remember, we were calculating P average. This is average power which is delivered to the resistor, which connected in the sinusoidal AC circuit. Now we look at the previous slide. We see here that this average, we want to find some equivalent DC equivalent current, which will give us the same average, will deliver the same average power to the resistor. And we can calculate it from this equation. So this current, equivalent DC current, which is called RMS current, will be equal to square root of P average divided by R. So now we substitute expression for P average here and get the final expression for the IRMS. So here is square root of I maximum square times R divided by 2 and R. So R and R cancel out, and we eventually get the expression for this RMS current, which is I maximum divided by square root of 2. So this is important parameter, this RMS current, since most of amperemeters, voltmeters, they are designed to measure RMS values of alternating current, and also is RMS is usually used in many equations in order to solve different problems. So I wanted to show you how we come to this point, to this kind of simple equation, but what we need to do, we need to calculate the average power delivered to a resistor in alternating circuit in the range of one period. And once we have it, we can easily calculate the RMS value of electric current, of AC current. Okay, so we are pretty much done with the resistor in our alternating current signal, and now we proceed further with inductor, which is a bit more interesting. So let us assume now another electric circuit, AC electric circuit, where we have inductor L. Here is again instantaneous voltage provided by the AC power supply is delta V maximum times sinus omega t. Here we have some instantaneous voltage across the inductor, which we call as delta VL. So again, according to Kirchhoff's loop rule, for instantaneous voltage drops, we can write the delta V plus delta VL is equal to 0. So now we can write delta, so instead of delta VL, we write minus L times DIL over dt. And this is equal to 0. So according to the Faraday's law, the voltage drop over inductor will be defined by the rate of changing electric current flowing through this inductor times to this coefficient, proportionality coefficient, which is inductance of the inductor L. And actually this current, instantaneous current IL, that's what we want to calculate. So we want to know what will be instantaneous current flowing through this inductor when we apply this AC voltage to it. So we can write now that delta V is equal to L times dIL over dt. And this is equal to actually what we apply. And this is delta V maximum times sinus omega t. And now we need to rearrange this equation in order to solve it for the DIL. So DIL is equal to delta V maximum over L times sinus omega t. So now, oh sorry, we forgot here dt. Now we need to integrate this in order to get the expression for instantaneous electric current through inductor. So here we just take integral and neglect with the constant, because constant is defined by initial conditions, but we don't care about them. We can choose any initial condition for this general case. So we need just to get the integral. And so here IL is equal to delta V maximum and L. These are constants. So we put them in front of the integral over L times integral sinus omega t dt. And the solution of this integral will be minus delta V maximum over L times, here we will have also omega, because we have omega in the argument of sinus, times cosinus omega t. So this is the expression for instantaneous electric current, and trigonometry identity tells us that we can substitute this cosinus omega t with minus sinus omega t minus pi over 2. So let us do this and substitute this sinus instead of cosinus. So we can continue on the next slide. So for instantaneous electric current through the inductor, we will have delta V maximum over omega L times sinus omega t minus pi over 2. And here next to it, I would like to write again the expression for instantaneous voltage drop over this, which we actually apply to the circuit, will be V is equal to delta V maximum sinus omega t. So we see that here is sinus and here is sinus. So they have both described by sinus function, but there is a phase shift between electric current and voltage. And it is shown here that electric current through the inductor will always lag behind voltage, by 1/4 of the period, by pi divided by 2, or so it's phase shift of 90 degrees. So in order to show it graphically, let me share the screen again. So we have again voltage and current as an inductor. So we see that voltage reaches its maximum value half 1/4 of period sooner than current reaches its maximum value. And the same with these phasors. There is 90-degree phase shift between voltage phasor and current phasor, since they rotate counterclockwise with the angular frequency of alternating current like power source applied to the circuit. Their angular frequencies omega are the same for voltage and current, but there is a phase shift of 90 degrees between these two vectors. And that means that always, as I mentioned ago, previously, electric current is lagging behind electric voltage in the AC over inductor in the AC electric circuit. So this is very, very important, and you should definitely remember this fact. So now let us come back again to our screen where we can write. And we need to consider maximum current, I maximum. So this is actually our maximum current. So this is equal to delta V maximum divided by omega L. So this denominator, omega L, is kind of opposition to charge flow for in alternating current signal in electric circuit. So this is something similar to resistance in DC electric circuit and also in AC electric circuit. That's why the units for the product omega L are also ohms. And at this point, the similarities are over because there is another important feature which has to be underlined. This opposition to electric transport of electric charge depends on frequency. So we know that active resistor is constant, is frequency independent. However, here this denominator, this product of omega L, here we have omega, and the higher frequency, the larger reactance of this opposition to electric charge motion. So that's why it is introduced a new term. It's called marked as XL. It's called inductive reactance, and this is equal to omega L. So this is frequency dependent inductive reactance. And now let us go a bit into the physical meaning of this. So why do we have frequency dependence of inductive reactance? So we know that from this equation, with increase of frequency, let's call frequency F, because angular frequency is equal to 2 pi F as a reminder. With increase of frequency, this inductive reactance increases. And That is because of Faraday's law. So we know that the induced back electromotive force, which kind of prevents change of the magnetic flux in the circuit, is proportional to the rate of changing electric current in the circuit. So if we increase the frequency, we automatically increase this rate of changing electric current. That means we increase induced electromotive force, and induced electromotive force has larger influence on preventing charge transport in the circuit through the inductor. That's why we get larger inductive reactance, and as a result, we get smaller current flowing through the inductor, because this inductive reactance is in the denominator, V maximum divided by XL. So this is important moment, that the opposition of for charge transport in alternating current circuit with inductor is defined by inductive reactance, and this inductive reactance is given by this simple equation. So it's proportional to the inductance of the inductor and angular frequency of the alternating current flowing through the inductor. So these are the most important conclusions and properties, like features of AC charge transport in inductor. And here I see we just didn't specify with a separate equation voltage drop over inductor. So instantaneous value of voltage over inductor. So this is equal to minus L d IL divided by dt. And now we know the concept of inductive reactance. So we can write that this will be minus I maximum times XL, the inductive reactance, times sinus omega t. So it serves as a resistance of active resistor, this inductive reactance, but it has a bit different physical meaning behind it. But mathematically, it also serves as a resistance, and we also measure this in the same units as resistance in ohms. Okay, so now let us consider one more component of alternating current signal circuit, and that will be capacitor. So we have some AC power supply connected to a capacitor C. So here we have voltage drop delta VC. Again, according to Kirchhoff's loop rule, delta V, this is instantaneous applied voltage, plus delta VC is equal to 0. And instead of delta VC, we know that voltage at the capacitor is defined by the ratio of electric charge accumulated at the capacitor divided by its capacitance. That will be delta V plus, oh, sorry, that will be here, minus Q over C, and this is equal to 0. So instead of delta V, we write expression for the applied voltage time dependence, delta V maximum times sinus omega t minus Q over C. This is equals to 0. And by rearranging, we can write that Q, electric charge, express it as a function of time. This will be capacitance C times delta V maximum times sinus omega t. So now, again, we want to determine what will be the instantaneous electric current flowing through this capacitor, or C. So in order to get it, IC will be equal to the rate of changing, to the rate of flowing of electric charge through the capacitor per time. That will be dq over dt. And then we take derivative of this equation. We will get omega C times delta V maximum times cosinus omega t. So this cosinus omega t we can represent in a different form. So let's do it here. Will be cosinus omega t is equal to sinus omega t plus pi over 2. Now we can write that this instantaneous electric current through the capacitor will be equal to omega times C times delta V maximum times sinus omega t plus pi over 2. So we see that there is some phase shift between voltage applied to the capacitor and current flowing through the capacitor. So in this case, current will lead the voltage over a capacitor by 1/4 of the period. So there will be phase shift of 90 degrees. But in the contrary to previous case, when current was lagging behind, now current is leading the voltage. So this can be seen here on this slide. So we have current reaching its maximum already 1/4 of period earlier than it happens for voltage drop over the capacitor. And there is again this highlighted this phase difference with phasors, these vectors representing voltage and current. Here, so previously we had current vector here, it was lagging behind voltage vector, voltage phasor, and now current phasor is leading voltage phasor, and there is also phase difference between them of 90 degrees, of pi divided by 2. So that is another important feature. So you need to understand what is the phase difference between, that there is no phase difference between current and voltage for active resistor. There is phase difference 90 degrees for inductor and capacitor. For inductor, phase electric current is lagging behind voltage. For capacitor, current is leading voltage. So these are fundamental difference between responses of different elements of alternating current circuits: resistor, inductor, and capacitor. So now let us come back again to this slide where we can write, because we still need to introduce the capacitive resistance. So, sorry, capacitive reactance. We had inductive reactance, now we have capacitive reactance. So maximum current will be equal from here, we see this, to omega times C times delta V maximum. This can be rewrite in a different form. Will be delta V maximum divided by 1 over omega C. And this is equal to delta V maximum divided by XC, which is XC is equal to 1 over omega C. And this is the capacitive reactance. Again, it depends on frequency, but what is important to understand that reactance, capacitive reactance decreases with increase of frequency. We have this frequency in the denominator. So let us try to understand what is the reason between this. First, we just write the expression for voltage drop over capacitor. So this is actually what we apply, V maximum sinus omega t, and this is equal to I maximum times XC times sinus omega t. So now let us explain why reactance, capacitive reactance decreases with increase of frequency. So first of all, it is good to, so let's write it here. C is equal to 1 omega C. Let's consider some extreme case when omega is equal to 0, then X C is like approaching infinity. It makes sense because we know that capacitor consists of two conductors separated with a dielectric. So physically, it's impossible to conduct DC current through a resistor. That's why if we go to frequency equals to 0, which is DC current, reactance, capacitive reactance will be infinity because there is no charge transfer through the resistor. So we increase frequency, so we go to higher frequencies, then what does it mean? It means that we can, per unit time, charge and discharge because we change polarity twice per period. So so we kind of charge and discharge capacitor 4 times per period. We go from 0 to maximum voltage, then from maximum voltage to 0, then from 0 to negative maximum, and then again to 0. So we charge and discharge. And the higher frequency, the more times per second we charge and discharge capacitor. And since electric current through capacitor is dq over dt. So this is the rate of transporting charge through the capacitor. If we charge and discharge capacitor more times per second at higher frequency, means we conduct higher current through the capacitor. And that results in smaller capacitive reactance, some opposition to, if we at the same amplitude of voltage conduct more current, means that the opposition for conducting, transporting charges through this capacitor decreases. And that happens because at higher frequency, we can charge and discharge more times per second per unit time capacitor, and eventually conduct more current and transport more charges. So that is the explanation why capacitive reactance decreases with increase of frequency. That is opposite to the inductive reactance, when we increase inductive reactance with increase of frequency because of Faraday's law. So they have different physical nature, this inductive reactance and capacitive reactance. But in the circuits of alternating current, they behave similarly, just the key difference is the phase difference. For the inductor, current is lagging behind voltage. For the capacitor, current is leading voltage. Okay, so we are running out of time already. And this is pretty much everything what I wanted to tell you during this lecture. Any questions?
No, thanks.
Okay, then thank you for attention and see you next lecture on Wednesday. We will continue with AC electric circuits when we have three components connected in series: resistor, inductor, and capacitor. I will see that they have some interesting features. So that will be our next topic. Take care and have a good evening. Bye-bye.
Thank you. Goodbye.
Thank you. Goodbye.
Mhm.